Hello. Good morning, everyone. I hope you're doing well. So what I want to do today is I want to spend today kind of reviewing some of concepts from Physics 111. We'll go through it fairly quickly. The other reason for doing this is because it'll lead us to talk about the pendulum, which we'll use for the first two labs, which, you know, there's no labs this week, there's no labs next week, but when we start the labs, I think it's the week of January 22nd. We'll do a lab 0, and then when you get to lab 1, we'll start doing this pendulum stuff. Okay, I'm also going to try, we'll see how it works. I'm going to try to record these lectures on Zoom, and then I'll have the recordings available. I'll put some links to them probably on my course website. We'll see how it works. I don't guarantee that I'll do it for the whole term, but if it goes smoothly, we can try it out. Okay, so what I want to do is talk about some of these concepts from Physics 111. In particular, we'll talk about equations of motion. And by that, what I really mean is Newton's second law, F equals ma. We'll draw some free body diagrams. We'll talk about a mass on a spring. And then we'll see how, if we convert some of our linear coordinates to rotational coordinates or angular coordinates, we can relate the mass on a spring problem to the pendulum. Okay, so we'll start with mass on a spring, and we'll see if we can derive its equation of motion. I don't know what the hell's going on over here. It's just noisy. We'll have to live with it for today, at least. Okay, so mass on a spring, what I want to imagine is we have, we have some horizontal surface, and there's a wall over on the right. We're going to attach a spring to that wall, and that spring will be connected also to some mass m. And what we'll say is we're going to assume that this is a frictionless surface. So the mass can slide back and forth without generating heat and losing some of its mechanical energy. Okay, so what we'll do is we'll identify a position, which I'm going to call x equals 0. And at x equals 0, if the edge of the mass is sitting at x equals 0, the spring is unstretched. So this is the equilibrium position. And so another way to think of it is this is the unstretched length of the spring. Okay, so obviously when the spring is not stretched, it's not pulling or pushing on the mass. If we stretch the spring past x equals 0, it's going to tend to pull the mass back towards equilibrium. If we compress the spring to the left of x equals 0, it will tend to push the mass back to equilibrium. That's why it's called a restoring force, because if you displace the mass, the force tends to restore the mass back to the equilibrium position. Okay, so spring force. We probably all remember spring force from Hooke's law. So Hooke's law says that as long as we don't stretch the spring or compress it too much, and by too much means that we don't want to permanently deform the spring. We want to allow it to come back to its original shape and length and all those things. If we don't go beyond that threshold, then the spring force is minus k times x. And so the minus sign just means that if we make x positive, the force is back into the negative x direction. If we make x negative, so we push the mass to the left of this x equals 0 position, then the force is going to be positive because we have minus k times x. but x is less than 0, and so we have a positive force. Okay, so if we write down Newton's second law, let's focus on the x direction or the horizontal direction. The second law, we can do a second law for the vertical direction, but in that case, we just have the gravitational force down that's completely balanced by the normal force up. So there's nothing really interesting happening there. So in the x direction, Newton's second law says the net force in the x direction is equal to the mass times the acceleration in the x direction. And now we just have to sum up all of the forces that are acting horizontally. But there is only one force in the horizontal direction because we've neglected friction, and that is just the spring force. And so we would just have MA along the x direction is equal to minus k times x. And so this thing is our equation of motion. So what Newton's second law tells us is the equation that's going to describe the motion of our object. In this case, what we're trying to do is we're trying to solve for how x behaves as a function of time. Okay, so we can solve for the position of the mass. And so that position would be labeled as x as a function. As a function of time. Okay. Well, let's see, what could we do? I'm just going to write down this equation of motion again. MAX is equal to minus KX. And let's see, acceleration is determined by how the velocity changes with time. And so we could equivalently write down the same expression as the following, where we've used that the acceleration in the x direction is the time derivative of the velocity. And then we could take it a step further. We could say, well, okay, how would I determine velocity? Well, velocity is the time derivative of position. And so I could say the velocity in the x direction is dx dt. And if we make that substitution, we would have m d by dt. And then for velocity, we would write dx by dt is equal to minus kx. And so, of course, we could write that as, instead of writing two first order derivatives, d by dt twice, we could say that's just the second derivative of position is minus kx. Or finally, the equation that I really wanted is two derivatives of position with respect to time is minus k over m times x. And so the goal here is to see, can I figure out some function of time that we're going to use for x, where after taking two derivatives of that function, I get it back again, I get that same function of x back, but with a minus sign. So can anyone think of some function where you take two derivatives, you get the function back, except there's a negative sign? Yeah, go ahead. Sine, yeah, sine or cos are both examples, so that's exactly right. So to find x of t, the time dependence of x, we require a function that after two derivatives with respect to time gives minus the original function. Okay, what I'm going to imagine is I imagine that we take our mass, we've stretched our spring, so some position, and then at t equals 0, I'm going to release it. So I want a function at time t equals 0 that is not at the equilibrium position. It's at some other stretched position. So I could either choose the sine or the cosine. But if I choose sine at t equals 0, like I get sine of 0, that's just going to give me 0. And so that would mean the position would be at equilibrium. On the other hand, if I take the cosine function, cos of 0 is 1. And so that would be displaced away from the equilibrium. So I'm going to choose the cosine function. So we're going to try, sorry. Let's give a try to try a solution of x is a cos omega times t. Okay, a is going to end up being our amplitude, and omega will be the angular frequency. And so we'll interpret those two in just a second. If this is going to be a valid solution, what we have to do is we have to take two derivatives and see if when we plug it into equation 1, do we get an expression that makes sense. So let's do dx dt. What's the derivative of a cosine function? It becomes a sine. We'll have an omega t. We'll still have the a out front. What am I missing? A negative. And what else am I missing? This. We're taking a time derivative, but inside the cosine function, we have some constant times t. And so that constant must multiply the outside. So we get this omega. So it's minus omega. A times sine omega t. And then we take the second derivative. Okay, this time we take the derivative of the sine function. Sine becomes plus cos. Okay, so we don't change the sign again, but we still have the negative sign from the first derivative. When we take the derivative of sine omega t with respect to time, we'll get another factor of omega. So now we'll have omega squared, then we have a cos omega t. Okay, but if we take a look here, x is equal to a cos omega t, and over here we have a cos omega t, and so this is just x. And so what we have therefore is two derivatives of position, with respect to time is equal to minus omega squared times x. And so what I want to do is I want to compare that to equation 1 at the top of the screen. And now equation 1 and let's call this new equation 2 are two expressions for two time derivatives of the position. And so they must be equal to each other if this is correct. So if x equals a cos omega t is a valid solution, we require equation 1 equal to equation 2. And so equation 1 has a minus k over m times x. So we have minus k over m times x must be equal to equation 2, which has a minus omega squared times x. Okay, good. So what we really figured out here is that this is going to be a solution, but there's going to be a restriction on the value of omega. And so we can figure out what that restriction is. If I look at this equation at the bottom here, they both have a minus sign, so I can cancel that. They both have an x, and so I can cancel that. And therefore, this omega is equal to the square root of k over m. And this is the angular frequency of a mass on a spring. And so let me remind you what angular frequency means. We all know what's going to happen with a mass on a spring. If it truly was a frictionless surface, I stretch out the mass and then I release it at some times, let's say t equals 0, I release it, and it will just oscillate back and forth. Because in any real setup, there would be some friction, you would be generating heat, you'd lose your mechanical energy, and those oscillations would die out, and the mass would rest at its equilibrium eventually. But if it was truly a frictionless surface, those oscillations would just continue indefinitely. And this frequency omega, this angular frequency, tells us how often those oscillations repeat. So let's recall the angular frequency omega is equal to 2 pi times f, where f is the number of cycles per second. The frequency was also related to the period of the oscillations. The period is how long it takes to complete one oscillation, and that's equal to the inverse of f. The period, capital T, is equal to 1 over f and is the time it takes to complete one full cycle or oscillation of the motion. Okay, so that means omega is 2 pi f is 2 pi divided by the period. And for our mass on a spring, we said that has to be square root of k divided by m. And so if we wanted to, we could solve for the period. And so therefore the period t is equal to, let's see, it would have to be 2 pi times the square root of m over k. So the period is determined by the mass of the block and also on the spring constant or the spring stiffness of the spring. So what we're going to try to do is we're going to try to see if we can relate this problem to a pendulum. So a string with a mass on the end of it, we displace the mass away from equilibrium and let it swing back and forth. And so that's exactly what you're going to be measuring when we get to labs 1 and 2. Okay, so let's see how far did we get. Here we go. All right. So let's try this. Let's try now the pendulum. Pendulum. We'll try to relate the problem of an oscillating pendulum to the mass on a spring. Sometimes you hear people talk about, I don't know, like the beauty or the elegance of physics. And I think one of the things maybe that they mean when they say that is that once you solve one type of problem, you can often take those methods or those insights and then apply them to problems that initially you might not think of as being related, but once you do a little bit of analysis, a little bit of digging, you begin to see that there are some parallels between these two distinct types of problems. And so that's what we're going to try to do here. And so for our pendulum, what we're going to have is, this will be like the ceiling, and then we'll have like a little pivot, and we'll attach a string to that pivot. And at the end of the string, we'll have our mass M. And if I drop down like a vertical reference line, what we can do is we can identify an angle theta. And theta determines by how much are we displaced away from our equilibrium. Okay, so if the pendulum mass is hanging straight vertically down, theta would be equal to 0, and that would correspond to the thing sitting at equilibrium. That's like the mass sitting at position x equals 0. Okay, and what we're going to do is we're going to say that our string has a length L. All right. So the first thing that we'll try to do is we'll try to draw a free body diagram. So free body diagram. So free body diagram for pendulum mass. Okay, the first thing I'm going to do is I'm going to kind of trace out the trajectory that this mass would follow. And what it's going to do is it's going to actually follow the arc of a circle. And that circle would have radius L. It's not going to trace out a complete circle, but it'll trace out, a section of the perimeter of a circle. So that's why, at the beginning I said one of the things we'll do is do a little bit of a review of rotational motion. And the reason we're going to be able to do that is because our pendulum mass is moving along the arc of a circle. So in that sense, it is undergoing rotational motion. Okay, so fair enough. What are the forces acting on our little mass? What's one of them? Gravity. Okay, so gravity near the surface of the Earth always points straight down. And so there's a gravitational force that would be mg. We're going to neglect things like air drag and buoyancy, but those things are happening. But let's imagine we can neglect them. What's another force acting on our mass? Tension, right? And tension is always applied directly along the length of the string. And so we have some tension in here. Okay. Now, so that's it. That's our free body diagram. And so now what we have to do is we have to make a choice for coordinate system. And there's no right or wrong choice. There's maybe choices that are more convenient than others, but as long as you pick one and you stick to it, you should be successful. I'm going to choose my coordinate system so that the x-axis is tangent to the circular motion that our little pendulum is following. Okay. The reason that I'm going to make that choice is because at this moment, our pendulum is either swinging to the left or the right, but its instantaneous velocity is going to be along that x direction. And so that's the reason I made that choice. The consequence of making that choice is that our gravitational force is now not along the x-axis, and it's also not along the vertical axis, where I'm going to choose it to be, of course, perpendicular to x. Okay, so that's the consequence. Okay, so what we're going to do next is we're going to break our forces or decompose our forces into components that are aligned with our coordinate system. And so let's decompose forces into X and Y components. Our tension is already along the y-axis, and so it has only a y component. We don't have to do anything with the tension. There's no component of the tension along the x direction. It's only the gravitational force that we have to worry about. Okay, and so what we should do is we should recognize that this angle between our y-axis, which is aligned with the string, and the gravitational force is the same theta that we labeled at the top. Okay, and so that means what we can do is we can say, all right, I'm going to have a component of my gravitational force along this y direction. It's in the negative y direction, and that is mg. Is it cosine or sine? Which one is cosine and which one's sine? The x is the sine, that's right. So remember SOHCAHTOA, right? So sine is opposite over hypotenuse, and so it involves the side opposite. And so if I was to imagine here a little right angle triangle, the sine is going to involve this opposite side, which is the side along the x-axis. And so this is sine theta. And then here, and I'm going to clean this up here. So let's see. Okay, good. And then SOHCAHTOA, ka is cos, is adjacent over hypotenuse. And so the adjacent side is a side that is next to the angle. And so that's the one on our y-axis here. And so we have an mg cos theta. Okay. And so once we've done that, like all the physics that we're going to do is really in setting up the problem and drawing this picture, choosing a coordinate system, decomposing our forces into components along those coordinate directions. That's all the physics. Once you've set that up properly, the rest of it is just a bit of algebra. Okay. And so let's do Newton's second law. I want to do the second law. Let's do the y direction in this case. So it would be the mass times the acceleration in the y direction would be equal to all of the forces acting along the y direction. And so if we look at our picture, we have the tension along the positive y direction. And then we have mg cos theta going down the y-axis. And so we would have minus mg cos theta. So what would be the acceleration in the y direction? Is the ball moving up or down the y-axis? No, it's moving perpendicular to the y-axis, right? That's why we chose the coordinate system we chose, is because all of that motion instantaneously is along the x direction or perpendicular to the y direction. So if there's no motion along y, what's the acceleration in the y direction? 0, okay? And so this is equal to 0 because there's no motion along the y direction. And so what this would tell us is therefore the tension must be equal to mg cos theta. All right, and so when you get a result like that, you can check some special cases to see if it makes sense, right? If our mass was hanging straight down, then theta would be equal to 0 and cos theta would be 1. And then our tension would just be mg. And that makes sense because when the thing's hanging directly down, we have the tension up, the gravitational force completely down, they have to balance each other, and so tension is equal to mg. On the other hand, if theta was equal to 90 degrees, then cos of 90 would be 0, and there would be no tension. And that makes sense because now the gravitational force is still down, it's always down, but the tension is vertical, and so the tension doesn't have to offset any gravitational force, and so it goes 0 when the mass is hanging at an angle of 90 degrees. Okay, so let's do the second law in the x direction. Okay, so second law says the net force is equal to the mass times the acceleration, in this case in the x direction. And then all we have to do is we have to go back to our picture and look at all of the forces that are in the x direction. And there's only one of them. And it's the mg sine theta component of the gravitational force. And so all we would say is this would be mg sine theta. Okay, sorry, I want to, in order for this to look more like our mass on a spring, I'm just going to flip the direction of the x-axis. And so if we do it like that, then we would say that mg sine theta is along the negative x direction. We didn't need to do that necessarily, but I want to make this look more like the mass of the spring. So we have that going along negative x. Okay. So now we have kind of a bit of a funny scenario here where we have some things that are similar to the mass on a spring, but some things that are a bit different. I could cancel this factor of the mass and I'd say the acceleration in the x direction is going to be 2 derivatives of the x position is equal to minus g sine theta. And so when I look at that, like it's not that similar to the mass on the spring, is it? Because for the mass on the spring, we had 2 derivatives of position was equal to minus some stuff times x. Here, I had my 2 in the wrong spot here. But now I have 2 derivatives is equal to minus, the negative sign's there, but I don't have an x over here. And so what we're going to have to do is we're going to have to make some manipulations to see if we can get this to look more like the mass on a spring example. So this is not quite the same as the mass on a spring. Let's see if we can make some manipulations. Okay, so to do that, we're going to have to take a little detour. So this little aside here is going to be so that we can remember some things about rotational motion. Okay, so what I want to think about is some circular motion where the circle has radius r. And so I'll try to draw the arc of this circle. Okay, so we imagine that we start with this scenario, and then this is, you know, the position of that point is somewhere along the arc at some time t, and then we wait a little bit of time, we wait a time duration of delta t. So at time t plus delta t, if our point is undergoing circular motion, it'll have moved to some new position along the arc. And so let's imagine that we wait some time and our new position is over here. And so the distance that our point has moved is the length of this arc. And I'm going to call, often people use S for arc lengths. Does anyone remember how do we find the length of that arc? How do you write down the length of S? If this angle here is theta and the radius is r, what's S? Okay, let's think of it this way. What's the circumference of a circle? 2 pi r. Okay, if I wanted to walk around the entire circumference, what is my angular displacement once I go around a circle once? 2 pi. So 2 pi is my angular displacement. I multiply it by r, and that tells me the circumference. All right, what if I walked half the circumference of a circle? What's my angular displacement in radians? Pi. What's the distance that I had to walk? Pi times r. So again, if I take my angular displacement, multiply it by the radius, that tells me the length of the arc. So what's the length of this arc S if my angular displacement is theta? R theta. That's right. So the relationship between arc length and angular displacement, theta, is just a factor of r between them. Okay, so then if we move a distance s in a time delta t, I would say my speed would be s divided by delta t. Or in the language of calculus, the speed is the time derivative of the position. Okay, that's fine, but the position S, we just said, is the same thing as r times theta. Is r changing when I move along my circular arc? It's not, right? If I'm moving in a circle, then the distance from the center is always the same. It's always just the radius r. And so r is a constant for circular motion. So we could say for circular motion, r is constant. So therefore v is, well, if I take the derivative of a constant times something, like the x derivative of c times x is just c times the derivative of x with respect to x. The constants can always come outside of derivative, right? And so this is just the same thing as r d theta dt. Okay, good. We're almost where I want to be. So we also know we also know that the acceleration is the time derivative of velocity. And, you know, when we want to tie this back to our pendulum, we had an acceleration on the left-hand side of our equation. So I want to know the acceleration of an object undergoing circular motion. Okay, so we take the derivative of the velocity, but the velocity we just said was r times d theta dt. And we also just said that r is a constant, so we can always pull that outside of a derivative. And so therefore, the acceleration is r times 2 derivatives of the angular position. Okay, so if we summarize all of this stuff, so summary. I want to compare linear motion and circular motion. So in linear motion, we had a position x. In angular or circular motion, what we talk about is like an angular position theta. And if we want to connect the two, what we had to do is we had to multiply by the radius of the circular motion. For linear motion, we had v is dx dt. And for our circular motion, what we're going to have is r times d theta dt. So the circular motion coordinate is theta. And so theta would be angular position, the angular speed would be d theta dt. And the angular acceleration would be 2 derivatives of the angular position, just like linear acceleration is 2 derivatives of the linear position. And then if we want to connect the two, linear motion and circular motion, it's always just related by a factor of the radius r. Okay, good. So that was our little aside. Now what I want to do is I want to go back to our pendulum problem. Okay, so let me draw the pendulum again. There was a ceiling, there was a string of length L, and then there was a little mass on it. And our little mass is undergoing circular motion. So, knowing what we know now, we can relate the acceleration along the x direction to our angular variable theta and the radius of the circular motion. In this case, it's the length of our string L. And we can say, therefore, the acceleration in the x direction is L d2 theta dt2. Okay. So again, it's just the radius of the motion times 2 derivatives of the angular position. And so what we're going to do is we're going to go back to before this aside. And I think we had equations 1 and 2. Let's call this equation 3. And what we're going to do is we're going to sub this new expression for our acceleration into equation 3. So let's sub this result into equation 3. And that would be L d2 theta dt2 is equal to minus, and what was it? It was G times sine theta. Okay, or finally then d2 theta dt2, let's divide by L, is equal to minus G over L sine theta. So this is our pendulum. Got pendulum equation of motion. And let's compare to d2x dt2 is equal to minus, what was it? Was it k over m, I think? Let's go check. Our equation of motion for mass on a spring was k over m times x. K over m times x. And so this is our mass on a spring. Okay, so it looks like they're getting closer together. They're still not exactly the same. We have two derivatives of some position variable. For the mass, position was given by x. For our pendulum, position is given by our angular variable theta. But whatever, two derivatives of something equals minus some constants, either g over L or k over m. But then the difference is, for the mass, we just had an x on the right-hand side, and for the pendulum, we have sine theta instead of just a theta. So they're still a little bit different because of this trig function that we have here. And so here is now when we're going to make our first approximation. And we're probably not going to finish this today, but let me show you what the approximation is going to look like. Let me just draw a big circle. Okay, I'm going to draw a big circle here. And what I'm going to do is, let's say that's the center of our circle. And this is the radius r. And I'm going to call this, say, point 1. And then I'm going to go to some other point, point 2. And what I want to do is I want to compare the length of this arc, S. Let's call this arc S. And we'll call this angle theta. In fact, actually, what I'm going to do, and you'll see why in a second, I'm going to call this angle 2 times theta. That's 2 times theta. Okay, so if our radius is r and our angular displacement is 2 theta, what's the length of this arc? It's r times what? 2 theta, exactly. Or it's 2r times theta in this case. All right, and then what I want to do is I want to compare that to this blue straight line distance between the 2 points. Okay, it's immediately obvious that the blue distance, the length of the blue line, is less than the length of the red arc. But I want to compare them. And so in order to make that comparison, what I'm going to do is I'm actually going to bisect this angle 2 theta so that this is now an angle theta. So I just cut that angle in half. And the reason I do that is now I can make a right angle triangle. Okay, and if I want to know the length of half of this blue line, what is it? It's r times, is it cos theta or sine theta? It's the side that's opposite of the angle. So it's sine theta. So this is, our sine theta is half the blue line. All right, so we know that the red arc, S, is longer than the blue line. And let me say the blue line has, I don't know, we'll call it a length D. So S is 2r theta, and D is 2 times r sine theta. So what that means then is that S is greater than D. That really means that sine theta is less than theta. Okay. So we have how much time? We have 30 seconds. So what I want to do then is I want to think about a really small angle, like a small theta here. And if we have this red arc and this straight line distance between the two, in this case, the difference between the red arc and the blue straight line gets smaller. So as you shrink theta down smaller and smaller and smaller, the difference between the red and blue lengths gets smaller and smaller and smaller. And eventually what you can do is say, for small enough theta, we can approximate the red and blue lengths as being the same. And that's going to help us solve our pendulum problem. Okay, so that's where we'll pick this up on Friday.